All right, welcome. This is part 2 of a 7-part series on Chapter 2 for the ME260 class. We're going to be talking about modulus of elasticity, yield, ultimate tensile strength, and ductility. So the first thing we're going to talk about is the modulus of elasticity. So if you recall from the first lecture, first part, we talked about the elastic portion of the stress-strain curve where it's straight. So that means the stress induced onto the sample results in an elongation that's proportional to the stress. And basically you get a straight line. So the slope of that straight line is called the Young's modulus, and also known as the modulus of elasticity. Young's modulus is defined as the slope of that curve, so that would be the stress divided by the strain. Okay? So we've got the stress-strain curve, we got the linear part of it, so try to think about that. And that defines a modulus of elasticity, which is a material property. Okay, and we get this again from the tensile tester. So think about this a little bit. What do you think the units are for the modulus of elasticity? So I'll give you a couple of seconds to think about it. You can pause the video at this point. Think about it some more, and when you think you know the answer, you can unpause and come back. Okay, so the units are going to be the same as they are for stress. It's a pressure unit. Okay, and that's megapascals. Pounds per inch, no. That's work done. And so the correct answer would be megapascals. And the reason is that we learn that the strain is unitless. And the stress is the pressure unit. So it's force divided by area. So it's the force applied to the test piece divided by the A naught, or the original area, cross-sectional area. Okay? All right. So the stress strain is the slope, as we mentioned. So here's a picture of it. So we have this elastic region, which is in blue. It's a straight line until the material starts to yield, and that's what happens at that point there. So let me get my fancy pen out right here. That's called the yield stress. So if we go across and look at the intercept, this is the stress, okay, applied to the material where it starts to yield. Okay, and that's called the yield stress, and that's usually a Y. And we talked about that in the other chapter a little bit and related it to grain size, okay, of the metal. Okay, and that's real easy to find. That's just the rise over run of the linear part of this curve. Okay, so I think you guys have got this. All right, next slide. So let's take a look at this, and this is kind of a summary from the last lecture. You know, as we're pulling on this system, we're in an elastic region, and then we start to go to a plastic region. So think about which is the elastic and which is the plastic region. And is it A? Right? The plastic region is what we're looking for. Is it A? Or is it this portion, B? So is it this part of the curve? Whoa, I can't draw. I'm getting a little better at it. Or this part of the curve? Which is the plastic region? I'll give you a couple seconds. You can pause and think about it. All right, the plastic region is where you get plastic deformation. And plastic deformation means that I'm deforming my material. It's not going back to its original shape. So that happens at this point right here and continues to deform. And if we stop at this point, for example, the material sometimes, not always, but sometimes will come back, but it'll be at a different length than when it started with. So there's a permanent deformation involved. Okay. So the elastic region is in A and the plastic region is in B. So how do you calculate the modulus of elasticity? Well, remember the definition is sigma, which is the stress, divided by epsilon, which is the strain. Okay, and that ratio is the modulus of elasticity, also known as Young's modulus. And the way you calculate it is you take the slope of the curve. Okay, and it's the slope in the elastic region. And again, what are the units? It's the same as stress. It's a pressure unit. So when I first learned about this, it was really confusing to me that a material property is in units of pressure. You know, as a physicist at the time when I learned this was kind of weird. You know, a pressure unit is a property of a material. But now, you know, studying stress-strain curves and understanding what's going on, now I get it. Okay. So the units are, again, for E, right, are the same as for stress, which are pressure units. So that's newtons per meter squared, or megapascals, or pounds per square inch. Okay, so here's another review. We've mentioned this at least 4 or 5 times now. So take a look at this curve and try to think about where does the material yield? Is it at A, B, or C? And I'll give you a couple seconds to think about it. You can pause the video. Okay. I don't think I'm going to tell you yet. What does it mean when it yields? This occurs when you transition from elastic to plastic. So that would be B. Okay, we're going from a straight line and we're starting to bend over. Whoa, I can't draw. And that's where you transition from elastic to plastic. What's the ultimate tensile strength? Where is that? Well, we haven't talked about that specifically. It's in the reading, so hopefully you've read ahead. It would be this right here. Ultimate tensile strength. So this is where it yields, right? This is Y. That's this point right here. Okay, that's supposed to be a Y. And then this point here, we refer to as ultimate tensile strength. UTS. Okay, so that's when it starts getting easier to pull this material apart. You can see it gets easier because the stress you have to apply to elongate it is going down until it finally does what? Breaks. So definition, UTS is at the maximum of the curve when the stress starts decreasing but resulting in continuous strain. This is seen when the material test rod starts to neck. So you'll actually see it start necking at that point. And where does the fracture, or where does the material fracture? Well, you know, when we're doing our testing on our tensile tester, it's recording the stress, okay, and the strain as we're pulling on this material. And at some point it breaks. So what ends up happening is the stress that it measures goes to 0. It just comes straight down. And that's the point where you know it's broken, because there's nothing holding it back anymore. Okay? All right. So we keep showing this offset in these graphics. So what is the graphics, or what is the offset all about? Well, when a material is soft and ductile, and you'll read this in the book, and it's easily bent like a spoon, right? You come into the region of plastic deformation pretty quickly on their curve. Okay? It starts to bend early on. And what you want to do there is you want to define that material in a certain way to show the material properties. So, it's hard to define where the yield stress is in materials like that, because it's like, well, when is it going to plastic? It seems to go to plastic in a region. So you might get, a curve. Say you have a very short elastic region, and then the curve starts to bend over a little bit, a little bit, a little bit, a little bit, and it does this kind of number. And it's like, well, where does it stop being straight and start being plastic? Well, the way you do that is you take a look at your curve, and then you go over by an offset, and then you run a parallel line to that straight part. And where it crosses, in this case it would cross here, that would be defined as your yield stress. So you define an offset, and usually it's 1%, or not even that much. It's usually like 0.1% or 0.02%, something like that, or 0.2%, excuse me. So, it just depends where you're working and what their definitions are. But, there are standards for different materials and whatnot. So the way you do it is you go 0.2%, delta, right, strain, and then you go parallel along the stress strain linear part. You go with the bulk modulus, you go up. And where it crosses, that's the yield stress. So that's when the material is defined to yield. And that's important when you're designing, right? You usually want to design down here in this region where it's linear, where it's elastic, because then if you design a part that way and you put some stress on it, it'll bend, but when you release the stress, it goes back to its original shape. So you typically want to design so that all of the forces and everything that your device will encounter is down here. It doesn't get much above this. If it does, if it goes all the way up to here, then you're going to get some permanent deformation in your part. So springs is a really good one, right? You want the springs to always come back to its original shape. Okay, so the extent of plastic deformation. So ductility is measured by the total elongation or area reduction at the fracture limit. You go, oh, what does that mean? Well, if you remember your stress strain curve, right, there's this straight part and then it curves over, right, and then it comes back down. Oops, comes back down. It's not drawing. Let me draw it over here. It comes back down and then it breaks, right? Well, this distance, this elongation here to fracture is called ductility. So ductility is a unitless number, but it gives you an idea of how long or how much you can stretch something. Okay, so the elongation is the final, that's when it breaks, minus the initial, divided by the initial length, multiplied by 100%. So the ductility could be, at 150%, or it could be at 50%, or it could be at 10%. It just depends on the material. Now, you can also define ductility as the reduction in the area. And if you do the math for this, the original area, the final area, remember it starts to neck in this region. This is where necking occurs. Okay, so it's starting to neck. So that means that area is getting smaller. So the area is getting smaller. That's area final. And it gets to a point where it finally snaps and breaks. Okay? These are equivalent. You'll get the exact same number if you look at the area or you look at the length. Can you do this? Can you guys prove this on an exam? The way to think about it is there's conservation of mass or conservation of volume, right? And it's not quite exact, but because sometimes the grains change a little bit and the distance between things change a little bit, you have some odd materials that don't follow that. But for the most part, for ductile metals, they're equivalent, okay? So you're stretching something, you're making it thinner and longer, all right? All right. So here's a typical table of materials, and we look at the yield strength, the ultimate tensile strength, and the elastic modulus. So remember, the elastic modulus is the slope of the stress strain curve. So if it has a higher slope, it's stiffer. That's something to remember. Okay, so if you want a stiff material for some applications, and other materials, you want it more ductile, you want it more flexible, more bendable, a lower Young's modulus or elastic modulus. Okay, and that's in pressure units, gigapascals, so you can see you have a wide range of stiffness. Tungsten and its alloys is very stiff. Okay, aluminum and its alloys is very flexible. So you're going to pick different materials for different design applications depending what you need. Okay, and now you can look at yield strength. So for example, tungsten and its alloys has a pretty high yield strength, but titanium is even better. Right? It may not be as good in stiffness, but maybe you want it more flexible. Whoops. You want it more flexible and you want it stronger. Titanium alloys are used sometimes in aerospace. Okay. The ultimate tensile strength, UTS, is the top of the curve where it starts. Remember, the curve kind of looks like this, and then it starts to bend over. The ultimate tensile strength right here is the strength or the strain, not the strain, the stress. It's a stress. UTS is a stress where it starts to fold over and it starts necking. Right? It's going to be necking. So now you're getting some severe deformation in the material. So you definitely don't want to design past the ultimate tensile strength unless you're designing something to fail at a certain stress. And you might do that. The stress gets too high, something breaks rather than something else breaking. Okay, it releases it. You might want something released at a certain stress. Okay, so we got ultimate tensile stress, yield strength. That's where it starts to curve over and become plastic, maybe at this point. Okay, and elastic modulus is the slope in this region right here of your curve. All right, so that's the way to think about these materials, right? So look at lead. It's got a really bad elastic modulus. It's not stiff at all. You just touch it and it bends and stays bent. Right? The yield strength, again, very, very, very low. Right? You can bend it very easily, and it yields. It stays in that shape. It doesn't return to its original shape. And the tensile strength, that means when you pull on it and it finally breaks, it's not very high either. Okay? So try to think about this. And then here's some other materials at room temperature. They usually classify these at room temperature. So if you're going to design something at a higher temperature, some of these parameters will change. And they do have tensile testers that have a furnace around it. So you take your sample, you put it in, the furnace closes around it, heats up to 700 degrees Celsius, for example, and then you start pulling on it and you see how it reacts. That's important if you're designing for inside of an engine, right? A rocket ship, that re-entry, those sorts of things. So these parameters are different at different temperatures. So be very, very careful when you're designing in the future for your company. Understand what the temperature ranges are, and then when you do your modeling, you want to be able to do it at those temperature extremes. And make sure that your system won't fail. Okay, so again, elastic modulus for different materials. We got ceramics and diamond. Kevlar, right? Those kind of things. Kevlar is very flexible. That's what this means. And diamonds are very stiff. Ultimate tensile strength. Okay, diamond is super high. 60,000 megapascals, right? That's when it starts to permanently change shape, and that's really hard to test. It usually will snap and fracture So sometimes the curve doesn't even go curve over. It comes up and then it breaks for brittle materials. Right? You never get to the point of plastic deformation. It just snaps. Okay, and then Poisson's ratio we're going to talk about a little bit later. And that's the end of part 2. I hope you enjoyed it. And, review the slides a little bit and take your